This meeting is being recorded.
Jacob, thank you so much for the introduction. And to all in the audience, welcome this morning of the 11th of May. So Jacob must have told you that I specialize in several complex variables. There is a fair amount of linear algebra that underpins this discipline at various levels. So what I'm going to do is present an eclectic mix of topics, which are fundamentally bits and pieces of linear algebra, whose motivations happen to arrive from complex analysis. And I shall hope that they are sort of all interlinked, and not necessarily because they are connected to several complex variables. They are connected to complex analysis. And I shall hope that it's not too eclectic a mix of topics. So I am, if you would allow me, I am going to begin with a concept in complex analysis that is familiar to you before I go from there to the underlying linear algebra. So it'll take me 10, 15, maybe slightly more, 10, 15 minutes, slightly more to get down to the linear algebra. So what I'm going to begin with is a very familiar definition. So recall this definition. So this is something that you've all seen. I have an open set in the complex plane, and I have a function f from omega to c. Let A be a point at omega. We say that f is C differentiable at A if the limit so this is something that's going to be very familiar to you. This is the limit of difference quotients as z approaches A, the limit of the quotient f of z minus f of A divided by z minus A. And if this limit exists, we give a name to it. So by definition, if this limit exists, we call this f prime of A. If this limit exists. And then we say that, so this is the definition of f differentiability. So the term I just defined is f differentiability at a given point. We say that the function itself is C differentiable. If f is differentiable at every A in omega. So this is all totally familiar to you. And then, by the way, I want to ask you the question, is the writing on the blackboard big enough to be discernible to all of you? Could someone just unmute themselves and let me know?
Sir.
Okay,
Yes,
excellent. Very good. Thank you so much. So everyone knows about this definition. And in fact, many of you would have seen right away that this definition is equivalent. That is the second term that I have defined. C differentiability is equivalent to f being holomorphic on omega. So what I want to do is look at this definition a little bit critically, because the point I want to make is, well, why do we care about this? And the point I'm going to make is that this is an attempt to generalize differentiability of functions defined on the real line. And this happens to be a notion of generalizing in mathematics, which would have been really bad. It would have been a really bad way of generalizing a concept, if not for the remarkable accident that this happens to be equivalent to holomorphicity. So if you don't mind, this is a definition that everyone is familiar with. I am going to erase this definition, everybody knows this, and write something that puts a little more substance to probably a slightly controversial sounding statement that I just made. I'm going to expand on the statement and I'll give you hopefully believable reasons why. So what is this definition good for? What's the above definition good for? And so let's do a pros and cons analysis. So pros. So one major pro is that C differentiability at A is the formal notion where we've just swapped out the real field for the complex field. Now, in general, just doing something like this and saying, I just did this and now let me try to explore. In general, this leads to pretty bad mathematics because you might not have a very rich theory by doing something that's simple-minded. But simple-minded as what I wrote may be, this is powerful at a certain level. So the definition, that is to say the definition that I gave, at a formal level, resembles the definition of differentiability of functions of one real variable. The only difference is with the field C replacing R, right? So maybe I should say this, replacing So you see what happens is, so the proof for various results like the sum rule for differentiability, the product rule for differentiability, and the chain rule, these proofs go through completely because at a formal level, I have the same concept with just the fields swapped out. So results like well, let's see, what are results? Like the sum rule, the product rule, and then the chain rule. Are automatic, are guaranteed. Okay. So I would imagine that whoever was playing around with in the early days of function theory, may have experimented with this very naive idea of just taking the definition that is classical, goes all the way back to Newton and Leibniz, of differentiation of functions in one real variable, and saying, now let me see. I'm going to replace the real variable by a complex variable. Since complex numbers form a field, a division is allowed, so difference quotients make sense. And so let's see what I can do. So this spirit, I'm afraid, pervades a whole lot of, say, the exercise of creating new mathematics by simple-minded generalization. It often results in mathematics that isn't necessarily very fruitful. But in this case, the simple-minded motivation, of course, had this big plus that the sum rule, the product rule, and the chain rule, at a minimum, we can name a few other theorems that are totally guaranteed. But one sort of hit the jackpot because the other major pro is C differentiability is equivalent to holomorphicity. So this is sort of the big payoff. And that is why when one is introduced to the subject of holomorphic functions, then one way of studying the discipline is to begin with the definition that I stated. So for the record, let me remind you, in fact, many of you, because of this statement over here, might be telling me that, well, I know that holomorphic functions are precisely those functions that were defined in the first few minutes of the lecture. But classically, this is how we define holomorphicity, which is that f being the function that I talked about right at the beginning, I'm going to write this function, I'm going to break this function up into its real and imaginary parts. F is equal to u plus iv, and where u and v are the real and imaginary parts, so they are R-valued maps, R-valued functions. So f is said to be the holomorphic Sorry about that. Board management is a bit of a challenge when one has a small blackboard. So this function is said to be holomorphic if, well, f is C differentiable, and the R2 valued map U comma V. So this is a map from omega to R2. So this is now a classical object. This is of class C1. Okay, so this is the definition of holomorphicity. So you see, formally, when we define holomorphicity, then there's a little bit more that is in the definition, but then they turn out to be totally equivalent. So that's where we hit the jackpot. But there is something kind of mystifying about this definition, and these are the cons. The first thing is, all of what I defined in the first few minutes of this lecture, it somehow it is not clear how it meshes with the classical notion of differentiability. I call this notion C differentiability. Why did I do so? And somehow one should realize, since this is an advanced instructional school, I think I'm allowed to make some of these value-laden statements that it is important when introducing a notion that somehow resembles or is adjacent to a classical notion, to try to understand how the classical notion is related to the newly defined notion. Okay, and classical differentiability, real differentiability, is an old notion. It is a pervasive notion. It pervades mathematics to a much greater extent than holomorphicity does. Okay, so it is kind of so the cons are, it sort of seems to mimic our differentiability naively. And what it does is it sort of attempts to mimic our differentiability for its own sake, and it is unclear how it relates to the differentiability of well, note that any complex valued map is at the same time an R2 valued map. And so we have the notion of the differentiability of maps in two real variables mapping into Rn. This is, as I said, a classical notion that has existed far before complex analysis existed and still pervades a much bigger chunk of mathematics. So it is a problem that C differentiability is the notion of, it is unclear how the notion of C differentiability is related to the differentiability of the R2 valued map UV going from omega to R2. Okay. And again, I remind you, what is U and V? What are U and V? U and V are respectively the real and imaginary parts of F. So this is a problem this should be a problem to any mathematician, because somehow one would expect a certain underlying unity of mathematics, which does not seem to be very apparent. But I guess the bigger problem is that the first definition does not, and I would say this is the biggest problem, does not admit generalization. Okay, how do I manage my board? Let's do it this way. Does not admit, I'm going to write it over here. Okay, does not admit generalization to F functions defined on open sets where your open set is now an open set in Cn, and n is no longer 1, but greater than or equal to 1. So everyone over here remembers the story of differentiability, right? How f dash, which is the derivative, if it exists, of a function in one real variable, how that notion generalizes to functions in several real variables, right? Everyone knows that story. Now, for very similar considerations, the definition of C differentiability does not seem to admit a generalization. Now, it becomes therefore all the more incumbent to try to understand the linkage, if there is any, between C differentiability and the classical differentiability of this R2 valued map. And hopefully we would see a path forward, right? So that is my preamble to what's going to come next. And I might take another 10 to 15 minutes before we hit the actual linear algebra, okay? So I'm going to step aside for a few seconds so that if people are taking notes and they're straggling, they can catch up. So a few seconds before I erase this blackboard. Okay, so let's get along with it. So without much ado, I am going to actually tell you that the column on the left was a bit of rhetoric on my part. It turns out that this simple-minded, this naive generalization of the difference quotients definition actually is equivalent to a definition that generalizes. And in fact, when I said that we hit the jackpot when we say that C differentiability is equivalent to holomorphicity, well, there is a reason for that. And the reason is that there are these intimate connections between this naive difference quotients definition and the classical differentiability of the underlying R2 valued function. So this is not yet linear algebra, but I think this is important to get out of the way, okay? Let me see if there's anything else I need to say to set the stage for this. No, I think I'm fine. Let omega be open in C and F, and this F is written as U plus IV is a function from omega into C. We understand that U and V are both real valued functions. So U and V are what we call the real and imaginary part. Let A be a point in omega. Then F is C differentiable at A if and only if. So let's write down an auxiliary function. So remember, I had said underlying any complex valued function is a vector valued, is an R2 valued function. Let's give a name to that. Let's call it F sub r. Let this be our provisional notation. So F sub r is defined as the map U comma V from omega into R2, right? So the theorem, the proposition says that F is C differentiable at A if and only if this underlying map is differentiable at A, and its total derivative. So I'm going to use the definition D stuck in front of the map of my interest to indicate the classical total derivative. So this map is differentiable at A, and its total derivative acts on C as a C linear transformation. Nice, huh? So this turns out to be, so there's this extremely natural linkage between the classical notion of the differentiability of the underlying real map and C differentiability. So let's look at the proof. It's actually very easy. It is, if you would stare at what I'm writing, it is simply playing around with notations. F is C differentiable at A. Well, if and only if, well, we write down the definition. If and only if there exists a number, a complex number A, and I'm going to write this A as alpha plus I beta. There is a complex number such that the limit as Z approaches A of f of Z minus f at A minus the complex number A times Z minus A divided by Z minus A. This limit is equal to 0. So all I have done is, if you have C differentiability, then F dash exists, right? I'm just calling this F dash a complex number. Oh, we know that F dash at A is some complex number. I'm just calling that A for certain private purposes. So now, this is really stupid, but let's do it. So this statement is equivalent to, there exists a complex number A such that the limit as H, so I'm now doing a change of variable. The limit as H goes to 0. Yeah, I acknowledge this step is kind of stupid, but it is the stupid but key intermediate step that allows you to establish a linkage between the two notions. So I have mod of H downstairs, and then I have mod of f of A plus H minus f at A minus A times H, the same complex number capital A times H, but I now put a modulus here. This is equal to 0. Okay, so now let's do some arithmetic. Okay, so this is sort of rough work. Right, so I have this H here, which is a complex number. I'm going to write it as H1 plus IH2. And so what happens if I have A times H1 plus I H2. I mean, this capital A is alpha plus I beta times I have this H1 plus I H2. So the purpose of this arithmetic I'm doing is to segregate this product into its real and imaginary parts. And everyone now knows this is easy, right? This is alpha H1 minus beta H2 plus I times the quantity beta H1 plus alpha H2. So this is baby arithmetic, right? So having done that, this above step transforms to the statement, there exists a capital A. This in terms of its real and imaginary parts is alpha plus I beta in C, such that the limit, okay, so now here is where I do something that is mildly non-trivial, but it is simply, I import this arithmetic over here. So what I do is, I do the stupid thing. I now pretend that I am, this computation now doesn't live in C, but it lives in R2. So this little h, I'm going to write this as the R2 vector H1, H2. And when I'm done with this, everyone will see why I was doing this. And so now, because I'm pretending that this complex number is living in R2, the absolute value, I write it as the Euclidean norm, same thing, right? Nothing has changed. So, but I told you, right, that the basis of this proof is just fooling around with notations. So this thing now actually becomes the map U comma V evaluated at A plus H. And just for fun, remember we have a second name for U comma V. This is just F at R of A. And then now let's write down what we get over here, because I'm now going to put in the outcome of that little computation. I need to do some space management, okay? So when I'm erasing this, I'm not doing this to say that I made a mistake. Let's just, I mean, the whole purpose of having invented a notation F of R is to be able to use it. So let's do that. So F sub R at A plus H minus F sub R at A minus, now here comes the thing, minus, this is going to be a vector. This is going to be a 2 vector. The first entry being the real part. So this is alpha H1 minus beta H2. Comma, beta H1 plus alpha H2. So this is a vector in R2, close braces. So I take the Euclidean norm. So kindly note the value of this apparently more complicated looking object is exactly the value of this up here. And so this limit is equal to 0. Aha! But do you see what I just did? Do you see that this is the image of the vector H under a certain real linear transformation, right? So C differentiability is equivalent to the existence of a certain real linear transformation from R2 to R2, so that this limit is 0. But that is exactly the definition of our differentiability. So to summarize, thus F is C differentiable if and only if the total derivative of this chap, this guy, the function or the R2 valued map f of R at A exists, right? And has the form okay, first let's write down the form. So a vector H goes to, well, it goes to the 2 by 2 real matrix with entries alpha minus beta, beta, alpha, acting on the column vector H1 and H2, right? But I want to say this is exactly to say that this acts as a C-linear transformation. Now, that is because any complex number, any C-linear transformation from C to C is simply multiplication by a complex number. So this is looking a bit nasty. So let me again do my board management a little cleverly. So this is equal to 0. But now, sort of the final step in my argument is to observe that the first coordinate is nothing but the real part of A times H1 plus IH2, and the second entry is nothing but the imaginary part of A times H1 plus I times H2, right? So this happens to be the last expression I wrote, which is in fact what the missing piece of the statement, that this thing actually, while as a thing, it is a linear transformation from R2 to R2, identifying R2 as the complex plane, that thing acts as a C-linear transformation, hence the proof, right? So let me, in fact, pause by the side of this blackboard and have you stare at this. And maybe this is a good time to ask any questions, people? Questions? No? Okay, very good.
Sir?
Then let's proceed. Yes, go ahead.
In case of classical differentiability over R, we have our differentiable map as R linear map.
That's right.
Now, in case of C, can we say that linear map will be a C differentiable?
So, I mean, if you are only looking at C-valued functions, and at the moment, you are looking at a function that is a function in one complex variable, the answer to your question is yes, which is precisely what we proved. At least that much do you agree on? First, this is the first step. This is not the answer to your question. Do you agree with that much? That for one dimension, for functions that are functions in one complex variable, taking values in C, we have proved that the answer to your question is yes. Do you see that much?
Sir, for one means f from C to C, it's fine. Let's say f is a function from C2 to C2.
Someone is talking over you, Vishwajit, right? Are you the one asking the question?
No, some background sound is coming.
Okay. Someone is unmuted. They might have to mute themselves. Yeah. So Bishwajit, if I understand your question now, what you were saying is if the domain omega. So we are now looking at the complex analog of classical differentiability, right? We are looking at a function in many complex variables, taking values into a complex vector space. Then your question is the relationship between C differentiability and the relationship is the relationship between C differentiability and classical differentiability going to be the analog of this? Is that your question?
Yes, sir.
Answer is yes, that's the next thing I'm going to do. Or I am going to do it partially. Yes, so the answer is absolutely yes. Very good question. And I want to sort of take the road to answering your question by observing that the second statement is generalizable to many variables, as you might have intuited. So let's do that. Okay, so I'm now going to erase this blackboard. And before I put substance to what I just said orally in response to Bishwajit's question, let me just highlight one point that drops out of this proof. And Bishwajit, I am in fact not going to give the complete details and the justification for the affirmative answer to your question, because that would take us away from linear algebra. Instead, what I'm going to do is present the key step in the mathematical proof that justifies the answer that I just gave. Okay, so that's how we are going to do things. Now, it's been my experience that on camera, if I have this much chalk dust, the writing becomes a bit unclear. So please bear with me. I don't like doing this either. It's a real pain in the neck, but for the sake of clarity, after about 2 or 3 erasures, this needs to be done. Okay, almost done. So let's highlight an important point. So this is a summary of what we did, right? So note that the second property in the above generalization. The second property, oh, why did I say above generalization? I meant above proposition. Can be generalized can be generalized to F defined on omega, taking values in C, where now omega is no longer sitting in the complex plane, but omega is open in Cn. And this is true for all n. So I'm probably stating the obvious, but the deficiency with the classical definition and this one, that is to say, the second property, is the following. You see, in the classical definition, we have to rely upon difference quotients. So if we are looking at the difference between the value of a function at a point A and the value at some increment. Well, if that increment is a complex number not equal to 0, then we can divide by that number, and that's where the difference quotient comes from. But if that increment is now some vector of small magnitude in Cn, then what the hell do you do, right? And in fact, this insight or this apparent obstacle underlies the way we define differentiability in the classical sense. And that insight overcomes precisely the obstacle that difference quotients present, and hence we have this. So I'm ready to give you a definition. And this is the definition of C differentiability for functions in more than one complex variable, and the way I'm going to define it. And this is a definition that will generalize C differentiability for functions in one complex variable. And the pathway to seeing that is the proposition whose proof I just erased. So this definition is now, let F, this is going to be written as U plus IV. Well, first, I forgot the most important thing. Let omega be an open subset of Cn this time, okay? N greater than or equal to 1, right? And let F, which is equal to U plus IV, be a map from omega into C, where, as usual, U and V are real functions, real valued functions. So we say that F is C differentiable at A and remember, A is a point in omega if the underlying R2 value map, F of R, this is the map UV. And again, I know I'm being very redundant, but just to make concepts, just to fix concepts, this is an R2 valued map. If this is differentiable, and I mean classically differentiable, at A. And the total derivative of this underlying map, so d of f sub r at A acts on Cn as a C linear functional. Right? I mean, if you think about what I just did here, f sub r is R2 valued, and so this total derivative is an R linear transformation from R2n into R2. So if this also acts C linearly, then the target of the C linear transformation is in fact C, which is why I use the word functional. So this is our definition. So you see what I did is the following. So this absolutely generalizes the familiar notion of C differentiability that you know from undergraduate complex analysis. And the way I arrive at this definition is from the proposition that I stated previously. C differentiability is equivalent to a certain property, and that property is generalizable. So this is C differentiability at a point. So now we say that, so I'm going to do something a little unorthodox over here. So you would expect the next statement to say that we say that f is C differentiable if it is C differentiable at every little a in omega, right? But I'm going to do something a little unorthodox, because that is what I'm now going to do is the stepping stone to an important introductory result in the theory of functions in multiple complex variables. We say that f is holomorphic. If f is C differentiable at every point a in omega. Okay. So in fact, I have defined for you what we mean by holomorphicity in many complex variables. And the point is, we have therefore created a concept which specializes to holomorphicity or complex analyticity, as you are all familiar with in the one variable setting. So I want to ask a question, because it may be possible that some of you are a little uncomfortable with what I just did. So I want to ask you, if there could be hands raised, that would be one way of getting a feedback. How many of you have seen some amount of function theory in one complex variable? Oh, sorry. So how many of you have seen some amount of function theory in several complex variables? In other words, how many of you are familiar, if at all, with holomorphicity in the multivariate setting? Could I have a show of hands? Okay, good. So that means when I did this, I haven't shocked anybody. And so let me actually write down a certain observation. And that what I do at the end of this observation would be the key step in the justification of my answer to Bishwajit's question. So you may have, I didn't see a show of hands, so I feel a bit awkward when I say this, but I'm sure you've heard this somewhere or the other and you're not remembering. You may have heard that f, so f is like above, omega is like above. F from omega to C is called.
Hello?
Yes? Yeah, tell me. Okay, it's probably someone speaking on the background. So this is called holomorphic.
সেইকাৰণেই মই ৰাতিপুৱা জলদি ওলাব দিছিলো টিকলিবা ওলাই তাৰপাছত
So it looks like someone is late and somebody else is telling them that they were warned to show up early. This is all very interesting. So you may have heard that an f like above is actually called holomorphic if given any a in omega, there exist positive numbers R1, R2, ... Rn. So So this omega, by the way, this omega is in Cn. So there exist these numbers. These are positive numbers depending on so my understanding is that these do depend on A such that F has a power series representation on a certain set, such that F of Z is given by a power series. So this is the summation. So now, since we are in multiple variables, instead of having n running through the natural numbers, you'd have a multi-index alpha running through the nth Cartesian product of the natural numbers. For each alpha, there is a constant C sub alpha times this monomial Z minus A to the power alpha. I am not going to elucidate what I mean by this because this is not going to be the focus of my talks. But what I mean to say is that you may have heard that holomorphicity is by definition the existence of a power series development, a local power series development. So I need to tell you where this equation holds. This is true for all Z in the following product of disks. A1, the disk with center A1, R1, Cartesian product, the disk with center A2 with radius R2, dot, dot, dot. The final Cartesian factor is A sub n, comma, R sub n, right? So let's give a name to this object. Let's call this delta of A. And of course, if I have a power series, then I should tell you about its convergence behavior, right? So I'm just going to continue this statement in here. Okay, so we have this continuing. So where the RHS converges absolutely and also converges uniformly to F on compacts of compact subsets of delta A. Now, this certainly feels like a very legitimate definition for holomorphicity for functions in several complex variables. Why so? Because one of the first things that we learn when we study holomorphic functions in one complex variable is that around each point A in its domain, there is a local power series development. So one legitimate way of defining holomorphicity would be to say that those functions are holomorphic, which defined on an open set omega admit a local power series development with all of the guarantees of good behavior, good convergence behavior of that power series. Now, I mean, this doesn't look at all like this definition, right? So the point is, the proof that establishes that this and what I defined are one and the same. The main point in that proof is the content of the theorem that I'm just going to write. And that would be essentially the key missing step in justifying that answer that I had given in the affirmative 10 minutes ago. Step. Key step in going from the last definition above to the power series development is actually this theorem. And I want to claim that this theorem is really a theorem in linear algebra combined with a basic insight that you have from multivariate real calculus. So the theorem is this, and the theorem is as follows. So let omega be open in Cn. N is now any positive integer. And f a complex valued function on omega. So if f is holomorphic, then del xj of u. So again, the understanding here is f is u plus iv. Del xj of u is equal to del yj of v, and del yj of v is del yj of u is equal to negative del xj at v, and this is true on all of omega and for all j going from 1 to n. Now, this should look familiar to you. And if it looks familiar to you, then you will probably be convinced that the key step in going from the last definition, which is about linear transformations, et cetera, to a power series development, that this is a key step, that assertion will feel convincing to you. I want to ask you, I claim that this should be familiar to you. Forget about these indices for the moment. What is the system of PDEs called?
Cauchy-Riemann equation.
Exactly, right? So these are a system of n, where n is the dimension of the Euclidean space in which omega is sitting. It's a system of n Cauchy-Riemann equations, right? So there seems to be something in the chat box. Let me see. Someone just answered in the chat, CR equations, excellent. So I want to claim that the above is an easy corollary of the following. So at long last, we come to our first linear algebra result, although of course in all of the definitions I have been making, linear transformations, or rather linear functionals, have been kind of implicit. So so this result, which is holomorphicity,
January,
implies...
February entrance exam is already over.
Okay, so this is a current, so I need to put a big fat line over here, because if you're going to be watching the video of this lecture and then you fell asleep and then you woke up at that point in time when this board is saturated, you might mistakenly think that what I have written here continues to this. So I'm putting a branch cut right here and saying the following. So this statement continues over here. This is sort of the main theorem of the day. Theorem. So this has got nothing to do with Cauchy-Riemann, C differentiability, and so on. So I'm going to write this. So writing this might take a little effort. Let Z, so Z is written as Z1 through ZD. Let this be in CD. Write Zj is equal to Xj plus I Yj, and denote this correspondence by, this is the correspondence between CD and R2D by this double-headed arrow. Now let script B superscript D. This is the bunch of standard unit vectors in a Cartesian product, epsilon 1 to epsilon d. Let this be the standard complex basis, standard ordered basis for CD. And so I'm doing a lot of notation setting. Script B, superscript 2D, R, and this is going to be in symbols E1, E2, dot, 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 E sub 2D. Okay, so this tells me I have another 15 to go. So let this be the standard ordered basis or I should say, the ordered basis of R2D with these identifications, with the identifications which is each epsilon j is by the identification of real coordinates with complex coordinates given this way is E sub 2j minus 1 and I times epsilon j has the identification E sub 2j. So j goes from 1 to d. Let T from R2D to itself be a real linear transformation. Did I miss anything? No, I haven't. Let this be R linear. Right? Let this be R linear. So now, since I put up a bunch of ordered bases, maybe you can guess I want to look at the matrix representation of this T with respect to this pair of ordered bases. And you would be, in fact, why am I doing just 2D to 2D? Let me be more general. Let me be more ambitious. Let's go R2N to R2M. So this is between vector spaces, not even necessarily of the same dimension. Let's be more ambitious. Let's do this. Let this be R linear. And let A be, A is the name I'm going to give to the matrix representation of T with respect to the ordered bases that I'm just going to name for you. So capital A is given as little a sub jk. So this is a 2m, notice the dimensions. So this is a 2m by 2n matrix. Let A be this matrix, let A be the matrix this is, you catch hold of this linear transformation and express it in terms of the ordered bases B2MR on the source vector space, B2MR on the target vector space. So this is the matrix representation of this T, okay? So this is the meaning of my A. Then T acts on, so remember, there is this identification between Cn and Rn, right? So T acts on Cn, which is identified with R2n by this identification for a general D. So when I take D to be equal to n, this up here gives me this identification. Then T acts on Cn, C linearly, if and only if the following relations hold true. Let's be careful now. If A sub 2j minus 1, comma 2k minus 1 is equal to A sub 2j 2k. And then I have another relation, A sub 2j minus 1 comma 2k is equal to negative A sub 2j comma 2k minus 1. So you have these relations, and this is for j running from, so j is the first index, okay? So this index is the rows of the matrix. So j should go from 1 to m, and the second entry index is the columns of my matrix, right? So k should go from 1 to m. So now let me actually give you the, before I prove this theorem, actually I'm not going to prove this theorem in full, okay? I am actually going to set the ball rolling for this theorem and have you work this out, have you complete the proof in tutorials. So now I'm going to, so the proof of the Cauchy-Riemann equation theorem is as follows. Right? And the proof is this. Fix a point A in omega. This is a totally arbitrary point, right? So apply the above theorem. And in this above theorem, you would be looking at the case where this m is equal to 1 with m equal to 1 to t being equal to, so remember which way the implication is going. I am given that f is holomorphic. So if I take an arbitrary a, then d sub fr at this arbitrary a exists, right? So remember, d of f sub r at a is an r linear transformation from r to n to r2. So r2n to r2, this is what I mean by m is equal to 1. So I apply this above theorem with t equal to this, right? So the CR equations, the Cauchy-Riemann equations, follow because the relevant partial derivatives, the partial derivatives are the matrix entries, matrix entries of the matrix representation for d sub fr. Hence the proof. Now, so you see, if I have this linear transformation and I take my real bases to be precisely what I described over here, then we can actually have a matrix representation for this abstract object. This is sometimes called a Jacobian matrix. This is called the Jacobian matrix. Not to be confused with the Jacobian, because the Jacobian with nothing after that is the determinant of the Jacobian matrix. So if this is a little bit hazy to you because you've forgotten your your multivariable calculus. In the tutorial today, we will actually begin with a review problem. So if this part was kind of is something that you forgot, then we will refresh your memory. Okay. So what I want to prove is this theorem, or actually what I want to do is do a partial proof. So to do this proof, we need to set up good notation. And then what I'm going to do tomorrow is to talk about a key aspect of this proof in a coordinate-free fashion, which is a notion known as a complex structure. But in today's tutorial, I want to actually set the ball rolling as to what a complex structure is. Okay, so this is only the start of the proof. Start of the proof. It is to be completed in tutorial. To be completed in the tutorial. Okay, so the start of the proof is, you see, so if T acts C-linearly, on Cn, for which we have a very specific identification with R2n, call this transformation. So remember, as a thing, as an object, T is an R-linear transformation. So if T acts C-linearly, it's actually, rigorously speaking, a different thing. So we call this different thing T sub C, okay? Then by the very definition of C-linearity, you would have T sub C acting on I times Z would be equal to I times T sub C acting on Z for all Z in Cn, okay? So this is an observation. So therefore, you see, at the level of real vectors, at the level of real vectors, for Z in, again, in CD, where D stands for either M or N, you see I times Z1 dot 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 Zn in the identification I had specified. Okay, so note Z1 is equal to X1 plus IY1. What is the impact of multiplying this by I? Well, you get IX1 minus Y1. So under my identification, this goes to the vector minus this vector viewed as an R2n vector is the vector minus Y1 X1, comma, dot 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 minus yd comma xd. So this right here is my definition of an auxiliary linear transformation, which I'm going to call JD. This right here is JD acting on the real vector x1, y1, comma, dot, 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 xd, yd. Right. So Jaydev, it's precisely 11 o'clock. But I noticed I started 4 minutes late, so could I take 4 more minutes so I can finish this thought? Yeah?
Yes, please.
Right. So we have this. Did everyone follow what I did here? Because this is kind of key. After that, it's just computation. Does anyone have a doubt? So you see, what happens is the way I have done an identification between an n. I should write D here. Sorry, I should write D here, right? So D is my dummy. D stands for either M or N. So if I have a D complex D vector, the identification of it with a real vector is the real part of the first complex coordinate will come first. Then its imaginary part will come second. Then the real part of the second complex coordinate will come third, and its imaginary part will be the fourth entry of the underlying real vector. That was my identification. So when I take Z1 and I multiply by I times the quantity x1 plus IY1, the real part of this is y negative y1. So that's why this comes here. And then the real part of I times Z1, sorry, the imaginary part of I times Z1 is x1. So x1 comes here, okay? So in this language, you see, so therefore T sub C is C linear, which is just a way of saying that T acts C linearly. To say that T acts C linearly is there is an auxiliary C linear transformation. This is to simply say that at the level of the real vectors, you have J sub M, J sub N acting on x1, y1, comma, dot, 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 xn, comma, yn. So this acting on this real vector composed with the real linear transformation is equal to T acting on the real vector x1, y1, comma, dot, 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 xn, yn, composed with Jn. So you see, this is just a transcription of this. You see, if I have a complex vector, I times that complex vector viewed as a real vector is given by this formula. So this part just encodes multiplication by I, and this equality tells us that the I, quote unquote, comes out, right? So this is what we have for all x1, comma, y1, comma, dot, 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 xn, comma, yn. This in R2n. So now, if you don't mind, let's at least do one one of the computations of this, and you can do, so now the proof is to compute. Proof is to compute. So let's do maybe one part of this computation. Which is, I look at the, let's say, 2j minus first row, or I look at the 2j minus first entry of this product. So we get, so let's look at the 2j minus first entry of this vector. So the 2j minus first entry of T composed with Jn acting on, well, this long thing. So this is a vector, right? And I look at this vector in the coordinates of the target space, which is B to M R. So this is, well, summation. So this is L running from 1. How many columns does this matrix have? This matrix has 2n columns, right? So L running from 1 to n, and you will have A sub 2L minus 1, comma. Oh, I'm so sorry. I'm looking at the 2j minus first entry, right? So I should have 2j minus 1, comma, 2L minus 1, okay? So this is, I am basically looking at the 2j minus first row of the matrix representation of T, and I am running down this vector. So we have a formula for this, right? So you see, at every odd position of JD acting on this, there is a minus YL. And then again, I am sticking to the 2j minus first row of this viewed in the basis that I gave you. At every even position of this, I have, so at every even position, so that is a 2L, I have an XL. Right? So I've given you one of the computations. So now what you need to do is you just need to equate this to whatever you see on this side. So I'm just going to say carry on, right? I hope you got the hang of how you do the arithmetic, right? We need to look at the matrix representative of this with respect to the basis I gave you. Now, you know that that is the basis we need to be looking at because that is the content of the conclusion of this theorem. Then you see what happens is when you rewrite this, when you write this as a column vector, then the LHS for every 2j minus first entry is this. So I've given you the reasoning and I've given you the computation. Now you would have to look at the other side. Okay, so that's how the proof goes. And in fact, the finish of this proof is a tutorial assignment. So with those words, I will stop for the day. I'll not erase the board, I'll step aside. Does anyone have any quick questions? Okay, so maybe Jaydev, that is it for today. People don't have any questions, so maybe we should just wrap up now, right?
Sure. Rajesh, you have to stop recording because you are the host now. So the other organizer is now dealing this.